Okay, good afternoon. So we're working here today on geometry. And we're going to pick up pretty much where we left off. We were talking about triangle proofs, and we looked specifically at one way to prove that two triangles are congruent, the angle-angle side postulate. And that's going to be an introduction to what triangle proofs kind of act like, what they're for, what we're trying to accomplish with them. Today's lesson, I'm going to focus a little bit more on the in-between pieces, like what postulates and theorems we're calling upon, giving them some names, giving them some examples so that we can have this toolbox at our disposal so that we can use it to connect different things together in order to get the logic of congruent triangle proofs together. So let's see here. Let's start out with the let's title this one Triangle Proofs Tools. Okay. Tool number one, called the reflexive property. In essence, this is a useful one in a lot of different ways. If it's not necessarily limited to this first statement of if two triangles, but really if two mathematical objects, if two triangles share a side or angle, those sides or angles are congruent. It's a relatively simple statement, but it's nice to have it be formalized here. We're saying that, the same thing is equal to itself. So for example, let's get the visual going here. We'll call this A, B, C, D. This line segment that's shared by these two triangles, one in red, one in blue here, that line segment, that side of those two triangles, is in fact congruent to itself. So when it comes to trying to show that the triangle ABD is congruent to the triangle CBD, it is useful to recognize that BD is in fact congruent to BD. It's also useful to understand that directionality, when it matters, the congruency still holds. So, note here a couple of things. One, it might feel, yeah, sure, that's easy to say, like something is equal to itself or congruent to itself. Good. But note that this is very specific. It has to be the shared side. It has to be perfectly shared. So for example, please excuse, it's not the easiest thing to use on this touch screen. For example, though, if we had this, there are similarities to what I'm drawing here, but hopefully it's visibly quite different as well, where this side is not congruent to this side, right? Despite them being shared, it's not shared in its entirety. In the first diagram here, this side is entirely the edge of both triangles, as opposed to, say, this side, which is the edge to only one of the triangles and then part of the edge of another triangle. That's important. Okay. Now the same can be said for angles, right? So we may see something like, for example, this angle shared between two triangles, this one highlighted internally, and then the larger triangle on the external there. Right, so that angle is certainly congruent to itself, and at times that's very useful for proving congruent triangles or not, but it's just these are ideas that we have in our toolbox. They're true whether or not the triangles are congruent, right? They're actually used at times in order to try to prove the congruence. It's not relying on the triangles being congruent. So for example, this triangle, I'm not, the two of them and the internal, I'm not sure that those actually are congruent triangles since I'm drawing them so imprecisely. If I was given some more facts about them, maybe they are, but that side is congruent to itself regardless. Hope that, it's a subtle thing, but hopefully that makes sense. So 2. So that'll be reflexive property number 1. So-called vertical angles are congruent. What does this look like? Well, we've seen this one a few times already on this channel. Give ourselves two parallel lines. And then two transversals that cross those parallel lines. Well, all segments in this case, to be precise. And please forgive any small imperfections there, so that is connected. What are we talking about here? We're talking about these two angles. Okay, they're so-called vertical lines. In prior, that's a name that you might come across, so it's important to know. But really what we're talking about is that they're supplemental to the same angle, the green one, right? So they add to 180 with the green separately, so they must be equal. In other words, let's call this angle A, we'll call this angle B, we'll call this angle C. Angle A plus angle C is 180. Angle C. Angle B plus angle C is 180. So you can do a nice algebraic substitution here. Angle A plus angle C must be, since it is 180, also equal to this. You can subtract the measure of angle C from both sides, and you get the proof there very quickly. But those are vertical angles. There are two lines that intersect. It doesn't have to be the setup of the two parallel lines cut by a transversal. It could be any two lines intersecting. Those vertical angles are congruent. I like to think about the word mirror angles, but vertical angles is more popular than that. Or folded angles. Okay. Let's see, have room to put number 3 here, yeah. So tool number 3, simple idea here, right angles are congruent. So we're often told that we have a right angle, for example, with this symbol, the little kind of box, that is telling you that that angle, so this type of thing, tells you the measure of the angle is 90 degrees. Perpendicular, another important word. So every angle you see marked by that symbol is congruent to every other one, right? Now again, here we're talking about congruence of pieces of triangles. The end goal here, often the congruence of the triangles, that's a goal to show. And these are kind of in-betweens or interim ideas, intermediaries towards that goal very frequently. But on the virtue of themselves, they don't separately show that triangles are congruent, but in combination, often they can be used to do so. Do a quick erase here. So we have the reflexive property, we have two angles supplemental to the same angle are congruent, or the so-called vertical angles are congruent. Another important one that we've dealt with already this will be number 4. Alternate interior angles are congruent. Running out of space on the side of the screen there. Congruent. But we must have the condition that those two sides of these triangles are parallel to each other. If we do not, we cannot say that alternate interior angles are congruent. In fact, they're not. So we get an issue here where this is going to be a very common given, right? Given two line segments are parallel to each other, prove some triangles are congruent. That is a crucial given because it allows us to do the alternate interior angles are congruent. Usually also gives us some vertical angles. So I think the most common setup is going to be this type of setup where you have two triangles that involve two vertical line segments combined with usually the definition of bisection or midpoint. What's necessary about this idea here, bisectors or midpoints, is they cut things in half, equal halves, perfectly in half, right? So we always need to remember here that when we're in a mathematical context, 1/2 is very, very precise. So splitting something in half in colloquial terms, if you're talking about like let's split some type of food or something, that's going to be a rough estimate. That's going to be let's cut it, right? And it's kind of half and half. This is not that. This is like perfectly abstractly cut in half, completely equal sides. And therefore, we get really two things. Another triangle for us. Now, one thing that's very common in mathematics is that the image can be a sketch, like in this case. But if the statement is made as a given, then we should discount the image precision in favor of the statement. So for example, this is a perfect example of what I'm talking about. This is a very common given. D is the midpoint of AC, or put another way, BD bisects AC. And what that tells us by the definition of the midpoint is that this is equal to that. AD and AC, AD and DC are congruent. They are equal length because we are told, in essence, they are equal length. There is a bit of annoyance at times for me that in the given statement we're told, say, that D is the midpoint of AC, as opposed to just being told that AD is equal to CD, which is equivalent in a lot of ways. That is the property of being a midpoint. The fact that D itself is the midpoint is only important in the fact that it determines that these two sides, by definition, are equal, congruent. The same can be said, and I'm keeping this under the same context here, about angle bisection. So if that angle is being bisected by the internal line, then those two angles are congruent to each other. You can maybe start to see like some of the pictures that we start to see when we think about congruent triangles, right? Like what types of situations might be happening that would allow us to show that two things are congruent. So let's do a proof or two to wind out the day. Okay, a little setup with some labels here. A, B, C in the middle, D bottom right, E. So it kind of looks like, I don't know, a bow tie, some kind of. We want to show, given two statements, that C is the midpoint of AE, and C is midpoint of BD. Show or prove triangle ABC is congruent to triangle EDC. So sit with it. Note that these given statements are likely not casual, meaning they are there for a purpose, they are there for a use. It's important that we know that C is the midpoint of AE. If we didn't know that, we would have to try to establish it. Or we might have to conclude that the two triangles are not congruent. But since we're given it, we know some things. Statement. Reason. Statement 1. Side AC is congruent to side EC. Why? Well, we just covered it a few moments ago. That's the definition of midpoint. C is the midpoint of AE. So as we look at the line segment A to E, it is cut in half if we chop at point C. Cut in half. For the same reason, though on a different line segment, BC is congruent to side DC. So you can see the two triangles we're trying to prove are congruent. We won't finish this off just yet, right? Because we don't necessarily know all the postulates that allow us to show that two triangles are congruent. And we don't know that AB is parallel to ED. Maybe they're not. But we do, in fact, know from today's work at least one other thing. Can you spot it? I want to make one more statement. That statement is that the angle ACB is congruent to the angle ECD. I'm talking about this angle. And I'm marking them with the number of hashes to just understand what we're comparing to each other. Why? vertical angles are congruent from earlier today. Or two angles supplementary to the same angle are congruent. What we will have here, starting next week, when we cover all of the postulates, is the side angle side postulate here. You can kind of see what it looks like, right? Side in angle then side, meaning the angle trapped by two sides, interior to them. And we establish congruence in that way. So these two triangles are in fact congruent by a side angle side postulate. Okay, so go over those concepts for yourself and make sure you understand how they can be used, how they show up, what the reality of given statements looks like, where we're given statements that usually lead us to some further statements. Like we're given these midpoint statements so we can make these statements very quickly by the definition of what we were given about the situation. So until next time,